project is called Voice Control Vacuum. My name is Natasha.
My name is Santosh.
My name is
I'm Jalessa Winley.
And our advisor was Dr. Joseph Pancrazio. In this project, we're going to give you a little bit introduction about our project. We're going to talk about some of the specifications that we had and how we control them. And then Mom's going to talk about the system architecture. We're going to show you a demo, and then Santosh is going to talk a little bit about the testing and results. We'll give you the total cost and time, and then we'll talk about some of the lessons we learned and feature development. So in our project was to develop a voice-controlled mechanism for a person living with significant disability. The reason we did this project was to give this person an opportunity to manipulate and control something just as well as any other able-bodied person would be able to do. So the focus is on the control mechanism so that it can be used for different mechanisms in the future. And our success is based on if this person would like to use the product when it's completed. So I want to introduce you all to our customer. His name is Stephen, and we'll be referred to Stephen from here on out. He attends the Stratford program. The Stratford program is a secondary school that hosts middle and high school students with an age range up to 22 years old who are living with different disabilities, some people with autism and other disabilities. So the Stratford program teaches these students educational skills as well as life skills for the future to give them opportunities to contribute to the communities and societies when they get out of school. Our customer, Stephen, his range of disabilities include limb spasticity, he has extensor, he's living with different motor disabilities, a lack of speech communication, he has a lack of directional skills, meaning that he can't really decipher between left and right, so he has to be trained by his caregivers and stakeholders, and he has a very, very limited reading level, so it's hard for him to, so instead of people saying left and right, he has to be shown the difference between left and right. And when he speaks, he's not able to say a range of words as we can. He has a very, very limited range of words that he's been trained to say with his speech therapist.
Okay, so upon graduating from the Stratford program, Stephen will be working at the Mount Vernon Lee Enterprise Corporation. This company was founded in 1971 to provide parents of 4 individual adults who are living with disabilities. They were looking for opportunity for their children upon graduating from a special education high school. This company provides these opportunities for these individuals to give back to society by providing vocational and day support services to these individuals. Stephen will be working at this site, and he'll be partaking in jobs such as cleaning. Here are a list of our requirement specifications. Upon working at this site, he will have assistants who will help him as far as cleaning. So making sure the device is placed in front of him properly, the device is turned off, and when he's finished using it, that it's turned off properly. So with that, the device needs to be able to be operational by an untrained adult. His power chair cannot be modified in any way. The device also needs to be able to differentiate the voice commands and display directions such as an arrow that corresponds with the command that will be given. Most importantly, the device should not possess any threats to the health of Stephen and others. And last, the device should be able to operate in a range of 25 feet, which is consistent with the workspace. So with that, this is a vision on how we wanted to help Stephen at the Mount Vernon Lee Enterprise. He will have a headset that will transmit data wirelessly to the mobile. So basically, he'll be controlling a vacuum through voice commands. Mom will discuss further the system architecture.
For the system architecture, we have level 0 architecture. When when we plan to see how the system works out, we decided that the inputs have to be power and audio signal input. The device must turn on the vacuum and turn on the LCD. The outputs are mechanical signal and display output. For the level 1 architecture, we wanted a detailed outline of the overall system. While the audio signal is processed through analog to digital converter and filter, the system will verify the process and send the data wirelessly. The receiver will receive data that in order to operate the device. Processing data will be sent to the LCD display, and the data will be used to drive the device to turn on the valve. For level 2 architecture, we have hardware is defined in the block diagram. The EasyVR Shield is a multi-purpose voice recognition module that is designed to add voice recognition to any application. It converts analog signal to digital and adds a filter. The Arduino 2560 is a microcontroller that will process the data in order to operate the device. It will send the data wirelessly through XP protocol. The XP protocol will send the data wirelessly to another XP protocol, and the data will be sent to a second Arduino 2560 in order to operate give commands to the Roomba. The Roomba is a robot that is capable of vacuuming on its own, but we reprogram it for Steven to give it Steven for manipulation and control. The LCD is processing data will be used to send to the LCD display to display graphics. The LCD will display 6 commands: on, forward, backward, left, right, stop. Transmitting circuit consists of the Arduino with EasyVR Shield communicating with XP. The receiving circuit is connected to the ROI connector to the Roomba and communicates with the Arduino 2560, which receives data from the XP module, the XP protocol. And the microcontroller will push data to the LCD display to display commands. We have a demo. Okay. Okay.
All of us are right.
Okay, now you're gonna try it again. Hold. Can you say ah? Okay. Good. Can you say ball?
Ball.
And recognize it. Yeah.
Mm.
Can you say ball?
Ball.
Okay.
Yes.
Pick up something. Can you say go?
Go.
Can you say I? Can you say I? Can you say I?
I.
Can you say I? Good. Ball.
Ball.
And that was an example of the training and how long it takes because of the differentiations of the space and the testing was in a smaller space because of the room that we were assigned to. But normally you'd be working in like a sport and health type center where you'd be cleaning an entire something like a yoga floor where there'd be optimal amount of space.
Since the voice recognition was the core part of our project, so we start with one of our team members. Once we integrate the hardware to train these 6 different commands: on, right, stop, left, forward, and the back. Then when we test it out with the normal user, Winley is one of our team members. The overall testing success was 79%, and we had no false positive results, and we had a low amount of false negative results. Once we tested with normal users, then we moved forward. Since our user cannot pronounce some of the commands like forward, backward, so we have to come up with some custom way that he's more comfortable with this one. So with the help of his caregivers, so we have some list of words. They are equivalent with the directional commands given to the algorithm. So here OMA means on, move system, and so on. So when we pick up these commands and we went to test it, we went to train those commands and save those commands on the memory of our EGBR, that's our voice recognition engine. So after we train those commands, then we tested these trained commands with our user Stephens, and our overall testing success rate was 40% and very low amount of false positive. We had only one false positive. When he was saying the code go, it was recognized as a ball. But when he said the ball, when he said the go again, it recognized as a ball. So that's one of the users we come up with. And we had very high amount of false negative results on comparing with our normal users, because when he gives the commands, he gets tired, he gets tired, and when the voice command is recognized, sometimes he gets excited and he starts producing sounds, and that's what we have done. And also we were dealing with the ambient voice on the room, because in order for our voice recognition, we has to be same, the train what I'm not speaking with. Okay, that's why if there is a voice, it doesn't matter. So once Spain and then I will choose.
Okay, so of course this takes a lot of time to develop and make a senior design project. So for each of us, here are our hours. Mom did 180, Natasha did 128, Santosh did 112, and I did 117. A total of 537 hours for the whole team. Here's our total cost, which is $804.08, and that is a combination of the team's contribution as well as the donations from our faculty advisor for the club.
And some future developments that we would do, we would further train the user so that he can further understand the directional commands. Because as of right now, he's being kind of fed the command to go left and right, so he would still need more training from his stakeholders. We would use better quality microphones so that the amount of false negatives would be much lower than they are. We would implement sensors so that when the Roomba approaches an obstacle, it stops. And we would develop a filter for the ambient noises inside of the room. These are references. Special thanks to Dr. Economidu, Dr. Fake Soto, and Dr. Schaefer, and Dr. Pancrazio. Questions?